All right. So I'm afraid the next speaker is me. I will check. Yeah. Okay. So now it's my turn to share the screen. So can you see the slides, please?
Yes, we can.
Perfect. And can you see if I use some kind of pencil on the slides? Is it visible?
That we can't see.
Oh, you can't see. Doesn't matter. Okay, I will explain in my words. Okay, so let's start. My name is Dalibor, and this talk is basically a report on our experience from practical system, where we have deployed so-called soft Walltime estimates, which is a feature in PBS Professional. PBS Professional is a standard HPC resource manager, and the soft Walltime, which was firstly introduced, I believe, in 2017 in the PBS Pro, its major goal is to replace user-provided runtime estimates for jobs, which are known to be very, very overestimated. The reason why user runtime estimates are overestimated is because these Walltime limits are used to kill jobs if they are exceeded. And because users don't want their jobs to be killed, they tend to overestimate them, which, however, is not good for the scheduler, because the scheduler then uses very overestimated runtimes to develop scheduling decisions. So the goal of the soft Walltime is to replace these user-provided estimates with something which is called soft Walltime. The soft means that this soft Walltime is not used to kill the job. The job is only killed when it reaches the original user-provided estimate. And the main idea is to use these more accurate estimates to improve the scheduler's performance, to improve utilization, decrease waiting times, improve chances of backfilling jobs, and so on. To illustrate this situation on a very simple example, on the left side you can see simplified standard scenario where there is a system where some jobs are running, some jobs are waiting, and there is a small window in the schedule where no job is.
Excuse me, Dalibor. I think you're not sharing the right screen.
Yeah, we can only see your first slide still.
Really?
Yes, I can see only the first slide.
Okay, that's weird. Thanks. I had previously some problems with the PowerPoint, so if I may, I will switch to Acrobat, and then I will try again. This should work, sure. So, how is it now? Can you see?
Yeah, we can see you switching them.
Okay, so, sorry about that. So, can you see the picture now?
Yeah.
Okay. So, okay, so again, simple example. On the left side, you see system that is using only user-provided Walltimes and is trying to place new job into the schedule because the job seems to be very long. The scheduler cannot use the gap in the schedule and must place the job at the end of the schedule. As soon as you start using soft Walltimes, there is a chance that the new job, despite the user telling you that it's long, your prediction will tell you, no, this job is actually short. So we will use these small spaces in the schedule to backfill the job, to improve your utilization, to decrease the wait time. That is the major idea behind using soft Walltimes. Of course, there are some problems when you start to use soft Walltimes because they may be underestimated. Your predictor is not perfect, and if the system detects that the soft wall time is not correct, that the job is actually running longer, you need to react. There's no problem for the system to extend the soft wall time. It does that automatically. The problem is that the original schedule that you have constructed using these soft wall times will become invalid, too optimistic. And all the reservations for top jobs and waiting jobs in the queue will also become invalid, and users will start to complain, which you don't want. So you must try to avoid underestimation of soft wall times as much as possible. Also, at least in our system, user-provided wall time estimates are used to route jobs into proper queues. So we have these short queues, long queues, and so on. And unless you enable job movement, the default behavior is that the job will stay in the original queue as assigned by the user-provided wall time, and for example, much shorter soft wall time will not cause that this job will be moved to proper queue. So this is something that you should be aware of if you try to use it. Also, there is no easy way to update soft wall time in PBS Pro. It's typically only set up when the job arrives or when the job starts, but not during the time that the job is waiting in the queue, which may be a problem if your predictor, for example, used some old data and in the meantime new data arrives. So these are somehow the limitations of the current implementation in the PBS Pro. The reason why we decided to try to use this soft wall time functionality was because our system, or to be more specific, our users are really, really terrible in estimating job runtimes. This figure shows in the blue line is the actual runtime or the distribution function of job runtimes, and the red line is the distribution function of user wall times. So you can see that the users are typically using only very few popular estimates, like 1 hour, 2 hour, 24 hours, 2 days, something like that. And the difference between the real runtimes is huge. Also, we did some previous research in the past using simulations where we saw that once we start to improve the estimates, the performance of the system is better. Better predictability, better improved wait times, and so on. So this was our motivation to actually deploy the solution in practice. The one thing that you need to develop on your own is the predictor. We decided to use, after some experimentation, we decided to use a very, very trivial predictor that uses information about previously computed user jobs to establish the soft wall time estimate. The good thing about this predictor is that it's very easy to implement. All you need to do is write some very short Python plugin in PBS. Then you will need a small database to store some data about the already computed jobs. And this predictor is very fast. So we can easily handle those roughly 20,000 jobs that we receive every day. It's not a bottleneck, so that's good. During the development phase, and the production phase, we tested 3 different predictors. We started the first deployment used absolutely trivial predictor that basically computed average value of 2 previous runtimes, and this value was used as the soft wall time, but it didn't work very well because it underestimated too many jobs. So we looked at the data and realized that if we add just a little time buffer to this original estimate, which was 15 minutes, we would solve a lot of problems. So the next predictor, version 2, it basically computed an average of previous runtimes and then added an extra 15 minutes, and it seemed to work well until we realized that we have several users that have highly varying job runtimes in one batch of jobs, which completely ruined this predictor. So then we threw it away and decided to deploy a third version of the predictor, which is used since December 2021, and it's still being used. Again, it's very simple. Instead of computing average, we compute the relative usage of job Walltime. What it is that we simply compute the fraction of actual job runtime divided by original job Walltime, which gives you a number between 0 and 1, and it expresses the relative usage of job Walltime. We compute this value for 15 previous jobs, then we pick the maximum, and by this factor we multiply the Walltime of the new job, and we add 15 minutes, an extra slack, and this number is the soft Walltime that we currently use in our system. Despite the fact that this predictor is really, really simple, it works pretty well, as you can see in the figure at the bottom of the page. We tested it on 6 different workloads from the parallel workloads archive, and the y-axis shows the average absolute error of this predictor compared to the error of the original user-provided Walltime. And the axis is in log scale, so we can see that the differences are quite high, and we were able to really decrease the error rates. Here I have some more detailed analysis of where the problems were in the respective iterations of the predictor, starting on the left with the first predictor and moving to the right are the newer versions. The interesting thing here is that these figures are box plots, so they show the shape of the distribution of estimate errors. And we also divide jobs into groups based on their execution time. So the red part in these figures are short jobs. The gray represent medium jobs, which means jobs that run between 2 hours and 1 day. And the blue ones represent longer jobs, so jobs running 1 day and longer. 4 weeks is the maximum in our system. And you can see that in the first, and within one figure on the left side are the error rates for users or user-provided estimates. On the right side are the errors of our soft Walltimes that we produced with these predictors. So you can see that the major problem was in that our predictors underestimate long jobs. It's clearly visible in the predictor number 1. We were able to decrease it somehow with the predictor number 2, but the solution that really became acceptable in practice is the predictor version 3, which is on the right side of this slide. This is not all that we did. We also tried to analyze whether these soft Walltimes actually help our users or help the system to operate more smoothly. But the proper way how to measure it would be to do simulations. But because we were, we wanted to test it in real life, we didn't perform simulation. We simply switch it on, and then we started to collect data and analyze that. Of course, such comparison is inherently flawed because you're comparing 2 different workloads, one with user-provided estimates that are used for scheduling, and the second later one is with those soft Walltimes. So these results must be analyzed with great care because, again, these are different workloads, different users computing different jobs. And also, sadly, there were several external factors that may play a major role in the overall behavior of the system and our users. Still, what we measured was waiting times in the real system, slowdowns. Slowdown is the ratio of job runtime to job, basically response time, runtime plus wait time, and system utilization. So we were interested how the system is utilized, how does the waiting looks, and whether jobs are experiencing slowdowns and which jobs are experiencing what slowdowns and so on. The workloads, as I said, were not identical, which is natural because they are from a real system. There were some similarities, some important similarities, like the system that we used to collect the workload, it was the same system with same hardware, same number of machines. The job parallelism between these two workloads was pretty similar. The overall utilization of the system was also quite similar, but there were also differences. The major difference that can be seen when comparing these two workloads is that once we, or after we started to use these soft Walltimes, we observed that the system is executing larger amounts of long jobs, which means that more CPU time is consumed by long jobs than previously. You can see it in this figure where it shows the percentages of short jobs, medium jobs, and long jobs, and you can see the difference. So this is a problem because it indicates that we are comparing, different classes of jobs. Also, what we realized is that the system has now more active users than had before we deployed these soft Walltimes into the practice. So, yeah, these are limitations. Still, here I show you on the left side comparison of wait times, and on the right side are slowdowns. In each box plot, again, jobs are divided into classes according to their duration. So short jobs, medium jobs, long jobs. And in each box plot on the left side is the workload where the jobs were scheduled using user-provided Walltimes. On the right side is the workload where soft Walltimes have been used. And you can see that there is a big difference. There is a big difference in the wait time distribution of medium jobs, which probably indicate that medium jobs that run between 2 hours and 24 hours, are good candidates to use soft Walltimes, because there is enough space to optimize the original Walltime, while the other classes also, you can see some differences. We have more long jobs, so it's probably natural that the wait time distribution is worse. But in our view, it's good news that short jobs and medium jobs now wait less time than previously. That's basically good news for us. In case of slowdown, excuse me, I just need to move the zoom panel. Again, the major differences in the slowdown, in the distribution of slowdowns for medium jobs. For the same reason, the fact that short jobs have high slowdowns is natural, because even short waiting will cause large slowdowns. So this is something that you would expect if you start to divide jobs into classes and measure slowdown. But these two figures were quite good news for us. This figure compares the utilization, so you can see that there are big peaks and low points. It's some of them can be explained. You can also see that the average utilization has increased since we deployed soft Walltimes a little bit, but I'm not 100% sure that this can be attributed to soft Walltimes. It can be, there are other external factors which I highlight here. So during the time that we measured this, we had 6 peaks of COVID, which may or may not influence how the system is used by our users. We also have periods where the utilization was low due to various holidays like Christmas and summer holidays. So, as I said, simply saying that the utilization is slightly higher is a fact, but it may not be directly caused by the fact that we've deployed these better estimates. I'm not sure about this. What also changed was the number of active users in the system. This figure shows the number of unique jobs and unique users during time. And since we have deployed soft Walltimes, we can see that the number of users is basically twice as high as was before. But the rise started before we deployed these soft Walltimes. So again, that's another point which just show you how difficult it is to draw conclusion from data that were collected in the real system that executes different workloads in different periods. Right, so to conclude, we believe that, or our report here is that it's relatively easy to deploy soft Walltimes in practice. The predictor can be implemented in 1 hour and its precision will be acceptable in most cases. Of course, there's a lot of, there are plenty of opportunities to improve the predictor, and we know that. But our goal was to, try it, see if it works. And so far, it seems it works. We have no complaints, except for few in the beginning, which we covered by new versions of the predictor. Everybody seems to be satisfied. And to bring you some firm results, I think I need to do 2 things. First, do some proper simulations, which means take the data and run experiments using the same data, but either user-provided estimates or soft Walltimes, or wait a little longer to cover at least 1 year and then compare two identical, time frames, not just 4 months against 8 months. The workloads will be made public, of course, and the implementation that is used in the PBS is available on the GitHub. So thank you for your attention, and I'm ready to answer your questions if there are any.
Dalibor, I have a question.
Sure.
Or it's more of a confirmation, I suppose. Am I correct that your third predictor for the soft Walltimes is still dependent on the submitter's original estimate?
Yes, exactly. Yeah.
Okay. Thanks.
Because that's the way it works in our system. So yeah.
Yeah.
Here it is. Yeah.
Gotcha. But, yeah. Okay. Thank you.
Well, yeah. The user is requested to estimate the runtime, because without that, the job can be executed, but will end up in some default queue, which I believe has 24-hour limit or something like that. So it's right. It's better for the user to try to estimate it as best as he or she can, but they're lazy, and sometimes it's difficult for them. Yeah, but another important factor is that in our system, the general rule is the shorter the queue, the more resources it can use, because very long queues have access to only a small fraction of resources in order to guarantee that your jobs will always be executed reasonably quickly. So,
gotcha.
I think you kind of preempted what my question was, which is what is the benefit of maintaining the user signal on the job length? But is there any interest in finding alternative methods? I mean, I understand why you're using it to sort of filter against queue, but is there a way to sort of look at things like queue length and use a different signal?
if I understand your question correctly, you mean to use different decision makers to route the jobs into different queues, or
so let me reframe the question slightly. I am incredibly cynical about user signal on things like job lengths, and so I mean, as you've kind of shown, there's not necessarily a lot of accuracy here. I was wondering what the actual benefit of keeping that user signal is, but if you're using it for filtering against particular queues and that's sort of about resource allocation, like that makes sense. I guess my question is, given that your findings are that the user signal is not particularly accurate, whether that's the path you intend to continue.
Oh, that's a good point. But I mean, to some level we have to, because currently we trust the user that if he or she says this job will run for 4 weeks, okay, are you sure? No, maybe, but we will keep our promise that okay, we will send the job to a queue that allows to run the job for 4 weeks, and we will try not to turn off the node, for example. But so we need to have some mechanism to divide jobs into groups that will then tell us which nodes these jobs can use. But if there is another method how to approach these jobs, that's a good question. I don't have the answer, but it's yeah, I need to think about it for a moment.
I do have a question too.
Yeah.
So through your data, you were showing that the type of jobs that were the most benefit from the prediction were large jobs first, and then medium-sized jobs, right? Is that correct?
I don't think it's a correct interpretation.
Okay.
The problem with these figures is that the details about short jobs, those are the red ones, are somehow hidden because the scale is preferring these blue and gray parts. But in my view, the best results were obtained for short jobs, but and there's plenty of short jobs. It's like 70% of our load, not load, 70% of our incoming jobs are short jobs, but not the load. But in the medium size, not size, but medium length of the job, that's where the difference was like clearly visible, because the predictor as it works now is stupid. And for example, it does not allow you to specify job runtime smaller than 15 minutes because we have this slack, this buffer there. So that's one limitation which does not allow you to produce really small estimates. And short jobs are 2 hours maximum. So if you think how we compute these predicted values, that we take 15 jobs, previous jobs, and then take the maximum of their runtime, and this uses as a factor to multiply the 2-hour wall time. Typically we will end up with something which is already close to 2 hours, but once you move to medium jobs, you have this scale from 2 hours to 24 hours, and there you can achieve bigger diversity, call it. Yeah. And more diversity means more the gaps will be different sized, and that's exactly what you want. You want,
yeah.
The worst thing is if every gap in the schedule has 2 hours length and all your jobs are 2 hours and 1 second. Then so you need this diversity, and this is something that we can improve in the future, because currently all jobs from one user that have the same wall time limit will end up with the same soft wall time, which is, it's not good, because again, you just, okay, so it will not be 2 hours, but it will be 100 jobs lasting for 1 hour and 37 minutes, which is maybe better, but not for that user particularly. So, yeah. But again, we simply wanted to try that and didn't want to bother with developing a perfect predictor, because we tried that with some machine learning stuff, and we spent 1 hour, not 1 hour, I wish, 1 year trying to learn this magical predictor to work for every data set, and we failed. So then we said, no, we threw everything away and we come up with this very trivial predictor, and it works to some extent.
Like, I was thinking that even if it's, you know, as you said, it's just a simple approach, shorter jobs are just easier to place, right? So jobs that are overly, like, super overestimated by the users will be easier to place the moment that you make them shorter for the scheduler perception. So that's going to happen. What I'm curious is what has the impact on more than long jobs. So you probably saw it, but I was like back and forth between my phone and the computer. The effect on large parallel jobs, or are there such jobs in this workload? Or it's mostly small.
We have,
because those are the ones affected the most by, you know, they're more susceptible to be affected by a single job it underestimated on length, right?
This figure, can you see these heat maps?
Yeah, perfectly.
So on the left side is a heat map where you can see the CPU requirements and job runtime, and on the left again is the workload from previous times, and on the right is the with soft wall times. So you can see that we don't have that much parallel.
I see.
Most jobs are in the range of 1 to 32 CPUs.
It's like a node or less.
Yeah, the utilization or these were job arrivals, but here on the bottom, why is it so slow? You can see that the, you know, CPU usage is not with those short jobs, but naturally with those running for long. But yeah, this system doesn't have large machines. The maximum size of machine is
right.
I don't know, 128, and then you have jobs running across multiple machines. But the typical
not that many.
Yeah, typical machine will have 64, I guess.
Yeah, and probably the very long ones, like the very parallel ones, are the very long ones, because they're like multi-week simulations and things like that.
Yeah, once the users you know, are able to actually run it without failing, then they will run it for long. So yeah.
Okay.
I think I should you know, oh, there is some question in chat.
No, that was actually me telling
Okay.
people if they can ask questions, they can use the chat, or they can use actually Slack too.
I will be available on Slack forever, so if someone else have some feedback, feel free.